sequence. Okay, so here up till I think the N implant we completed, right? Or no? I think N-well masks. I think we have progressed up till a much level. I think PMOS for fabrication, we did, and MOS fabrication, annealing we did, contact cuts we did also. And the metallization, I think still we are metallization, metal 2, both we did actually. We completed up till that we were left to do from the overglass and pad opening things. Okay, from there we were supposed to do. So let's start the class from here, and let me share the screen and let's start. Okay. Yeah, before starting, give me 1 minute. I will be back. Please provide me 1 minute. I will be back. Hello, I am back actually. So we can start. Okay. Okay. So we ended up last class with the metal 2 connection. So how we did the metal 2 fabrication thing. So metal 1 and metal 2 fabrication we understood in the last class, and here we understood the CVD process with its chemical vapor deposition, and up till here how the contact masks were done. After that one, how the metallization process took place. The first starting with the process like metal 1, metal 2, these are the way actually it grows up till the maximum possible metals what is available inside the layout. So first it's done with the metal 1 masks, then after it is done, then it is made with the metal 2. Another layer of LT or CVD oxide is added, via openings are created in that one, and metal 2 deposited and patterned. The way actually all the designs have been patterned in this one. Okay, so is my voice audible to you guys? Hello.
Yes, sir.
Yeah, okay. So now in the CMOS fabrication sequence part, over glass and pad opening. Okay, a protective layer is added over the surface. The protective layer consists of the layer of SiO2 followed by a layer of silicon nitride. A silicon nitride and a layer of SiO2 is put, the protective layer also is there over the designs, so to protect it. Okay, then the silicon nitride layer act as a diffusion barrier against the contaminants and uh, against the contaminant. So any contamination, any outline part, sorry, outside particles come across that one. That Si in layer and the layer of a SiO2 will protect it. Okay, that's a protective layer is given on top of that one. Finally, contact cuts are each over the metal 2 on the passivation to allow for the wire bonding. It is like when metal one is drawn, all the things connections are patterned, then they on protective excuse me, protective material is given on the top of that one. Then on the top of that one, using the CVD process and the patternization, the patterning techniques, they do the metal to connection so that the metal one, metal two doesn't get uh, sorted actually there. Okay, so that is the actual insulation. It works as an insulator between the metal one and metal two, so that they doesn't get shorted actually. That is the reason this thing is done. So this how this pad opening things and the protective film is given on the layout. So in the interview, the interviewer will not ask you this thing that in the pad opening. So if you tell that how metal one and metal two is fabricated, in which the say protective material is provided on the top of the metal one and between the and below the metal two, so to prevent them from getting shorted, then it will be a good edge on your interview, that he or she will think that you know that up till this level, because generally no one tell this particular point. It's a very nominal and very minute point. Okay, so just you can just put it on the interview when you're discussing the fabrication parts. Okay, now coming the yields. Okay, so yield is equal to number of good chips on wafers divided by total number of chips. Okay, so it is like when the wafer is done, when the wafer, let me show it to you in the paint. It will be easy for you to understand. 1 second. When you are drawing, suppose when there is, let me, when suppose this is a wafer. Okay, this is a wafer. You have done lots of designing, all sorts of things, in which you will see only at this area part only couple of chips are available. Okay, in this part only chips are available actually. Okay, in which you will find, suppose let me show you, one, two, three, four. Okay, one, two, four. Okay, remove that, finish. Okay, so you will find this area, particular area only, is having the number of chips which have been fabricated. Okay, in this a particular area is having only that thing, this particular area only. So our usable area is this only, where the chips have been fabricated with different with the process. But when there after it is done, it is being cut down. Okay, a thin blades will cut these chips, a thin nano blades will cut these chips. Okay, it will cut these chips so that individual square size chip block comes out, and then it is been fabricated inside the plastic packaging, so that which can reach you to you guys. Then you can use it in your different circuit designs or in your CPU. But what happens while connecting this while cutting these chips, this wafer, what happens, some chips are not cut down properly. Suppose if this is should be a perfect chip, this should be a perfect chip. What happened, due to the plus minus 5% error, the chip suppose was supposed to be this one, but due to cutting, what happened, only this much came out, this much, this part left off. Okay, this much were left off, or it got shot out due to the cutting of this one. Okay, so this thing happens. So in this one, the yields formula, it calculate the number of good chips. So total, suppose here are 1 2 3 4 5, 1 2 3 4 5, 5 cross 5, 25 blocks are there. Okay, in which 20 are the good chips, 20 chips are good chips. Okay, like who is this guest, can it anyone tell me? Hello, hello, who's this guest
Yes,
one?
sir. Yes, sir. Yes, sir.
Like can you tell your name? I'm not getting you.
Nageshwar, sir. This is Nageshwar.
Oh, okay. I'm not getting.
There
So
is a,
sorry,
yeah.
Nageswar.
So fine. Issue with
Mhm.
my thing. That's the thing I could not join.
Okay, okay. So, suppose 25 in which are 20 are good chips. These are these are good chips. Good chips. And five devices, suppose five are bad chips. Bad chips, it does means it doesn't what doesn't that doesn't mean it works. But while the cutting, this was not cut down properly. Suppose this row was not cut down properly, so it become got damaged. If you cut it between from this part, suppose if you cut this chip part from here, what will happen? It will get separated. Means the connection, everything got cut down due to the saw cutting. That is the reason it is calculated the number of chips, good chips, by total number of the chips in the wafer. Okay, this is how we can find the bad chips in the wafer. Okay, that is what it actually denoted here. So if you come across this one yields, y is equal to number of good chips on wafer by total number of the chips. The yield is influenced by the technology, the chip area, the layout. Okay, scribe, cut, and packaging also contribute the final yields. Yield can approximated by the chip area, which is in centimeter square, by the defect density, defect divided by centimeter square. Like the chip area, suppose this is a chip area. Okay, suppose we have this kind of a chip area. Suppose let it be, I'm just saying it at 2 cross 2. It's a 2 cross 2. Okay, after this one you will be finding that then you will find that a 2 cross 2 chip area is there. Then the defect density, how many number of defected chips are there. Okay, by with that centimeters, how much wastage have been happened. So these five chips which have been got damaged, this was also an area. Okay, so that will be calculated and it will be checked. That is actually called yields. So this is the formula of the yields which is actually been used. Let me highlight it with a different color. It will be great to do. So okay, so this y is equals to e power minus root under a into d. Okay, so this formula, for you guys don't need this formula actually. This is the foundry formula. Just you have to remember that y else is equal to exponential to the power minus root under area multiplied by area of the that area of the chip multiplied with the defect density. So just you have to just remember this one, nothing else you have to do. It is, you won't be able to calculate these things, but only you can tell them that you can use this formula to get the value of the yields actually. You cannot, so you can explain them that these are the number of, how the I explained that this is a wafer in which suppose total 25 chips are there, in which 20 are good chips and 5 are bad chips. So 5 if have them some kind of area, then what will that, the total chip area means individual chip area. Suppose individual one to the other 20, 2 cross 2 if 2 cross 2, what is the area of the single one? If you get the area of the single one, then you can multiply it with the 20. So if you get the 20 value with the multiply that one, you can put in this formula actually. You can put in this formula in the place of a, and then you calculate the d values. D is density of chips. So number of the chips in the density area multiplied by the number of defected chips. Then put it here. You will be getting that particular result. So this is how it is been calculated yields. So if may anyone asks you what is yield, you should be able to tell the answer that yield, sir, this is the yield. And what is yield? Yield is y is equal to, yield is equal to number of, it is the formula to calculate the number of good chips on a wafer divided by the total number of chips. So it means if suppose 25, just make an example. Just if there is 25 chips over all the wafer, in which 20 are good chips and 5 are bad chips. So that's the value which yields actually give us. Okay, so what is yields are influenced? Yield is influenced by these three parameters. The techno, I think, let me take a good color. Actually, I'm not okay. That this color will fine. Okay, the yield is actually influenced by these three parameters: the technology, the chip area, the layout. Okay, the scribe out actually packaging also contributes the final yield. So you should be able to tell this particular things. Okay, this particular things you should be able to tell the uh, interviewer that these are the points are influence that these are the points influences the yield actually. Okay, so this question will for sure majority of the interview this will come. What is yields? It's a very basic question. Okay, you need to remember this one. Now come the design rules. The design rules. See, after the fabrication all steps are done, like we have been discussing the fabrication for a long period of time. So now if I tell you that we have been done, we have suppose a inverter, let me correct it to you. Suppose we have an inverter, we are getting fabricated. Okay, you guys had made an inverter which has to be fabricated. Okay, so this is the A, this is the Y, this is the VDD, and this is the VSS. Okay, now you will be fabricating this guy. Let me do it here. So this is our substrate, and let me write it here, P sub here. Then what I will do, I will be in the bulk connection, then the, sorry, like this it should be, then it should be like this, then it should be this kind of thing. Okay, so in this one it should be P plus N plus N plus. We are using high dopant. If it is N minus, then it will be less dopant, and if it is no plus or minus, then it is no doping is there. Okay, so P plus and N plus. Okay, here our N well should be there. Here should be our N well. This is our N well. Okay, you have fabricated all these things. Now you are putting a small, let me put one small guy here, which is our oxide layer. Okay, we're putting a oxide layer at this level. We are putting a oxide layer, SiO2 we are putting here. Okay, after this one we are trying to fabricate our source, gate and drain on the top of this one. So how we will be doing, let me show you. Okay, let me recapitulate it. Okay, so if we come across this part, here, let me, okay, and then if I try making this gate connection here, if I try making the gate connection here actually like this. Okay, and in the top of this one I put a gate. So this should be actually your, source. Okay, here it should be also like this actually, not like that. Okay, one second. Let me cut it out. Okay, let me like this. Okay, then it should be your drain, then should be your drain starting here, again a gate, again a excuse me, again the source, and here it should be your bulk connection, here also be your bulk connection. Okay, bulk connection properly. Okay, you have been fabricating this. Okay, in the top of this one you have been putting a layer which is responsible for metal connection. So you have done only with metal one connection. Okay, suppose you have done this one with metal one connections. Okay, let me put the metal one connections like this, then let me put one also here and then one also here. Okay. Now I will be putting blue color inside the metal one, guys. I will putting the blue colors in this one. So we have given the metal one also here for the gate to make from poly to metal one. Okay. Then like this we have done, sorry, like this we have done our metallization process. We have done the metal connections, all sort of things. Then what happened in the between also, we have to put this connection metal. Okay, we have to put this metal connection in the between also, because drain should be connected. If you go to the schematic, the drain here is connected actually. Okay, let me go to this one and let me put this one here. It is drain connected. Source going in this side, source going in that side. Bulk is already sorted. You do not need to touch that thing. Bulk is already sorted inside the P substrate. You do not need to touch anything. Just to show that one, I have put that bulk connection symbol here, which will be make you easy to understand. Okay, let me put one. Okay, so you have been done all these things, connection done. So suppose this inverter you have been fabricated, you have given TSMC that please fabricate my inverter over a big wafer size. Okay, so you need suppose 100 chip in a suppose 200 that chip size, that thing they will be doing your chip design, because it's a inverter is a very single block. They will do, they will be putting all the chips in a, wait 1 second, they will be putting all the chips in your wafer like this, and then suppose they will be start fabrication. Okay, in which suppose 100 chips came out. I'm unable to make 100 chips here, so just consider this as a 100 chips only. Okay, 100 chips you have been designing. You have got the 100 chips like this, okay, in which 20 sorry, 10 chips are wastage, in which total you have, suppose you have to explain to the interviewer like this. So total, they, while making this cross section, you have to explain the interviewer what are the process. First we will do the anvil, then we will do the diffusion, then we will be fabricating the polysilicon layer. Then I have just directly drawn all these things. Okay, you have to explain first a substrate, the doping will be there, then anvil we will be drawing with a mask connect with masking, then we will go for the implants actually, then we will go for the diffusion and the polysilicon. Okay, done all the masking stage. You have to tell that first we will be putting SiO2, then we will be making a mask, putting the mask, we'll put the light on the top of this one. If photoresistive material will be there, which will help us to etch that thing, and after that one we given like HF or nitric acid, then it will go out, and that particular design will came across, will get embossed on the substrate. You have to explain up till the metallization part. After it is done, you can go to the this yield part. You have to tell that one, suppose we have given this number of things, in which total we have 100 chips in our this wafer, in which total 10 chips are defected. How it can be indicated? Due to the cutting, the sometime plus minus 5% error, machine error. If it's not a human error, it's a machine error. If the chips got by mistakenly cut well, in a larger part, and the chip got defected. So we will be using that formula with the total number of good chips divided by by the total number of chips. Then you will be getting that particular ratio. So that is what actually yields is. You have to explain the interviewer in this fashion, then only you will able to complete the whole fabrication step. Okay, so is it clear now how you will be explaining all these things in an interview? Hello, hello, is I'm audible to you guys? Hello. Okay, okay, okay. Is it clear? Are any doubts? Okay, okay, okay. Then comes the design rules actually. Okay, in the design rules, the limitation of patterning process give rise to set of mask design guidelines called design rules. Okay, so in the, what are the design rules? What we do in our DRC na, these are that actually the design rules actually what we try to follow. That we are trying to explain here. The design rule, the limitation of patterning of the patterning process, like let me show you. Suppose you are giving a this kind of suppose you have a mask which is a N-well mask. Suppose N-well need to be fabricated, okay, but the N-well has to have a measurement, okay, that the machine has that capability to fabricate a N-well mask at that level only. So that is what actually how design rule comes into picture. Suppose the angle of light, how the light, what should the wavelength of light, so that decides the overall measurements of this N-well, that decides the overall measurement of the x and y of the n well, how it is and that design things is written inside the that design files. Okay, let me show you the design files how it looks like. I think you haven't seen that design files yet. Let me show it to you how the design file looks like. Let me turn on the cadence and let me show you the design files. How does it looks? I think you will be able to understand. Excuse me. Let me show you the design files. 1 second. Till that time, let me. Okay. So the design, which is called the design rules are set of guidelines that specify the minimum dimensions and spacing allowed in a layout drawing, which you run the DRC, it only flags those kind of errors. So violating a design rule might result in a non-functional circuit or in a highly reduced yield. You mean understood this? If you go with the DRC, we would make a design when each which you have multiple DRC rules are violated, and if you go for the fabrication, the reduced yield should be will be higher, and non-functional circuits might be there because the device, the machine in the fabrication lab will won't be able to fabricate at that capacity because it is not calibrated at that level. So it won't be able to fabricate. So it has able to fabricate up till this level. Suppose if it is able to fabricate only maximum at this level, oh, sorry, if it is capable of fabricating maximum at this level, but your device design is up till this level. So then what means, suppose at this two part, suppose some critical designs are there, then what will happen? If this part is unable to fabricated, that means it is then means your design will not work, means it is violating the design rules. So you have to make the designs as per being inside the design rules only. Okay, let me show you the design rules, what are how the design rule looks like actually. Okay, if you go to the cadence here, and let me go to the home and let me go to cadence GPTK 90. Here you will able to see. Let me go to Ashura. In the Ashura, you will find DRC a rule file which we use in our DRC deck actually. We have DRC, the DRC rule file. Here, if you double click this guy and type display, you will be seeing a big kind of text file is there. Okay, so this is the actually design rules which you use in your design. So if you type here, so very common is a metal one. If I type here M1 and try to find it, you will be getting, I think, let me check that. Okay. Metal 1 to metal 1 spacing, I think M1.W1. Let me try finding it. Okay. M1.W1. Let me try finding it. Okay, I'm unable to find that one. Okay, so let me find that one. You will be seeing that metal 1 to metal 1 spacing or metal 1 to metal 1. I think that is much at below level. If you go to the DRM and search that kind of do anyone have the DRM in the front of them? Can anyone tell me that metal rule? I will able to search it for you. If anyone have that DRM, because I don't have the DRM in front of me now. Okay. ETL metal. This should go fine actually. Metal 1 to metal 1. Okay, so these are the actual rules which you generally use in your design to read the tool read this kind of designs, and it tells you that these are the values which you should be maintaining as per the DRC deck actually. This is called a DRC deck. Okay, so it has been written by some guys in the industry. It's in skill language actually. Okay, so if you see here, it's n implant 0.1, n implant to oxide overlap must be greater than and equal to 0.13. This is the headline which comes to you if you flag the if you violate the DRC, it will be flagging on your tool actually. So this is all actually all the uh, uh, errors actually which comes. So this is the details error which you should be maintaining in the fabrication, that is actually taken care in the fabrication part. Okay. So design rules can be expressed a list of minimum feature, size, and spacing for all mask required in the given process. Okay. So interviewer might asks you what is DRC and what kind of error you can see in the DRC deck. Okay. So you have to tell DRC is the design rule checker, which is responsible for checking the DRC rules, which is provided by the foundry, that which it checks the design's robustness and the design's what I can say, the design's capability, that the it is it able to satisfy the design rules given by the foundry or not. The design rules are the maximum the minimum dimensions or the spacing that the fabrication machineries can fabricate for you over the wafer. That is actually is try to given inside the DRC, and in that level on and in that boundary only you have to do your designs being inside boundary. Okay, so what are the kinds of DRC you can see? You can say to the interval spacing related DRC is there, then edge to edge spacing, then dimension related spacing, then corner to corners, vertex to vertex spacing. Then you can tell some example like n-well to n-well spacing should be these, m1 to m1 spacing, m1 to m1, sorry, m1 to m1, sorry, m1 width actually, m2 to m2 spacing, then implant to implant spacing, oxide to implant spacing. These are kind of a spacing which you can find in the design rule. Then via spacings, then via enclosure size. These are all the things is given inside the design rule, and the design rules is available inside the design that DRC deck. For Ashura it is design.drc.rule. Caliber, if it is mentor caliber, then it will caliber runset.drc. These are all the things which is designed by the foundry and written in the that deck file, which we use in our tool to check the DRC violations for the layout. Okay, based on single parameter lambda that characterize the linear feature. Example, the minimum grid, the lambda based rules allow simple scaling. These rules what we use in our deck actually, these are actually called lambda rules. The distance between, suppose, n well, sorry, let me write it as NW to NW spacing. Suppose we have 0.3 micrometer. We can represent this as 0.3 lambda. Minimum, this should be actually the N well to N 0.3 lambda. These are actually called the lambda rules. The measuring values between the spacing and the dimensions in the DRC design rule deck, that is measured in lambda actually. Okay, that is what actually called the lambda rules. We try to make it draw it in micrometer. Here it is actually because the machines understand lambda values, because if you go and check the wavelength of a light, if it is the wavelength formula, you will find the lambda that thing inside that one. That is the reason it does with the lambda rules. Okay. So that is the reason it checks with the lambda rule. If you see that I forgot the wavelength formula. Let me check once. What is the wavelength formula? If anyone remember, can tell. Anyone remembers? Okay. wavelength is equal lambda is equals to V by F. Lambda represent the wavelength, V represent the wave speed, that speed velocity, and the f frequency f. So that lambda is actually that machine's parameter which is responsible that wavelength, because the machine comes draw the lithography light that comes in the UV light or the lithography laser light that has a measurement of a lambda thing. That's the reason actually these lambda rules are used here. Okay. So these are the design rule things. Now come to the design rule. Suppose the minimum width and minimum spacing is actually denoting here the minimum line, the smallest dimension permitted for any object in the layout drawing. This is the minimum. Suppose if you have seen, excuse me, if you have seen the metal one, okay, in this one our metal one has a minimum. If you see the minimum width when you draw a metal one simply using the command p path, you will be seeing the minimum values, which is actually I think 0.12 micrometer. So 0.1 to the minimum spacing you should be maintaining, because below that one the machine calibrated for a 90 nanometer technology won't be able to fabricate it. If you make a 0.10 micrometer, you can make it, but the machine will only be able to fabricate it. Okay, it cannot go down till that level. So that is the reason 0.12 micrometer minimum spacing is maintained for the 90 nanometer PDK. Okay, so what, and this is the minimum width of this one. So the minimum spacing, so minimum spacing means suppose two metals are running side by side like this. So the machine's calibration is done in such a way that it should maintain the spacing actually. Okay, so if the spacing is not in between, the spacing between these, it should be 0.12. If I'm not wrong, that 0.12, so that in 0.12 only that machine will able to read it. Below that one also it won't be able to run. So that is the reason this kind of spacing and minimum width things are done here. Okay, so minimum spacing, smallest distance permitted between the edge of two objects. If you see here, between the edge of two objects. Okay, this rule originates from the resolution of the optical printing. What I told, that machine's capacity. This term, optical resolution, this is the scientific term which is used for the machinery, optical resolution of the optical printing system, the etching process or the surface roughness, the optical, these are the machine's calibration, machine's capacity you need to be knowing. So how the rules are originate, if anyone asks you how the rules are originated, the rules are originated from the optical printing system. Like what is the capacity of that UV light or the lithography light, that is called optical resolution of the optical printing system, then the etching process and the surface roughness. These three parameters decide the rule what you use inside the DRC deck. Okay, now if I go to the next step of the real rules, the contact and the vias. Contact and the vias, minimum size limited by the lithography process. Same, this is also have the same concept that that design rules, the contact and vias are limited actually by the lithography, that optical resolution, etching, and a surface roughness. Large contact can result crack and voids. So crack and voids actually is a term used here. So if you are using a very large contact, it can happen this kind of crack and voids can come. Dimension of contact cuts are restricted to values that can be reliable manufactured. So everything depends upon those three parameters only: resolution of optical printing, etching process, and surface roughness only. Those things only decide what should be your design size minimum, what should be your design in spacing, minimum spacing only. Okay, what should be the distance from edge to edge, spaced vertices to vertices, diagonal to diagonal, then minimum spacing, minimum width. These are all things are considered inside the design rules. If you get a time, if you read this text file, you will get all those DRC rules which are available inside the DRF, because this is a raw file. DRM is an explained properly manner file. In that one, it has been explained properly. If you see this, suppose this rule, it is explained properly. What does it actually says? Okay, that this rule actually says that n implant to oxide overlap must be 0. Above 0.1 is micrometer. Okay, this means the NVL to oxide overlap measurements minimum spacing should be this one. Okay, so that thing is explained properly in a DRM. That is why DRM is given, not this deck at file actually. If the deck file is given, many of the guys won't be able to understand. In that one, with examples, all these things are actually provided. Okay, now if you come to the design rules again, P MOSFET rules like N plus and M plus P plus regions are formed in two steps. That same thing again explained here. At the active area openings allow the implants to penetrate into the silicon substrate. The N select and P select provides photoresist opening over the active area to be implanted. So these are all the design rule concepts which have been explained here, which we generally design inside that one. I already explained these all things. These are some much more minute details how, as per the design rules, the designs are being done. So these are actually being done at this process. Okay. So if you come across this again, gate overhang, this thing, that same that gate design will be there. After this design rules, they will be following. These are the same steps, and again, you can just read these steps and get to know what are the things happening inside this one. Okay, now comes the other process, the PWell process. The same thing is again repeated here. Okay, so you need actually to understand the design rules. So the design rules are actually up till here fabrication, whether this machine does that, does this. Here the design rules, it is explaining how the design rules are responsible, what are the responsibility of the design rules, how the response design rules are helpful to create the optimized designs which are able to fabricated inside the industry. That only things are explained here. These are the techniques, actually large contacts and results to cracks and void. These things you should be knowing, very which are minute things. In the interview, no one will ask you in this much depth detail. They will only ask you up till the maximum metallization process or the maximum yield process. That maximum process they will ask you up till the year, starting from the ingot method, that Skrolaski method, how to make the ingot, that crystal wafer, then up till maximum the metallization process, that what is the metal to, and maximum if you go to maximum yield process. After that, no one goes, no one will go, because because it's a very huge topic. No one will come in that one. They will, after, in between only, no one will come up till the maximum metallization 2 also, metal 2. They will just tell, okay, okay, I understood that, means he is done with this topic, he don't want to know more. He just checking only your flow. If your flow breaks, means he will understand that this guy don't know. So you should be confident when you are giving the interview. Then you should be confident actually while telling, okay, okay, this step happens in the Spolarsky method, wafer formation, doping, then in well, these all things you should be telling the interviewer in a summarized way. No one want to listen history there. You should be try to explain those up till the as much as you can, till he don't tell you to stop. Come up till yields and stop it. Then don't go after that one, or you can stop at metallization 2 also. Okay, metal 2 or metal 1 fabrication, wherever it is, you can stop. So just tell them. The interviewer, majority of the time, interviewer tell, okay, okay, maximum he will go up till that polysilicon fabrication. He will tell, okay, okay, stop. I understood what you are trying to say. He will just go. He will then go to the FinFET fabrication. He will check some knowledge of a FinFET fabrication, that you have or not those things. So this how the fabrication. If anyone question, guys ask you a question, what is related to the fabrication, you should be able to explain. This kind of question will be asked you in the interview. I will be giving those like what I can say, mock questions, which will be helpful for you to understand what kind of exact questions comes in the fabrication, in the for from fabrication in the interview. Okay, so now if there are any questions, you can ask me. If there any question, you can ask me. Hello. Nilani, Nanda, Nageshwar, Hiranmai. Hiranmai, did you get the things today? Might be something be heavy for you because you can open your mic and you can tell, Hiranmai.
I understood, sir.
Is it okay for you? Did you watch those videos?
Yes, sir, but after 25th September, again there are videos from October 3rd only. What about the videos in the between, sir?
I need to check. I need to check that one because I need to check that one. Might be I not remembering. So I think in between that suppose 2-3 classes we have like 3-4 classes we haven't done. Okay, so I have to check those. But this much big gap will not be there. I think some understanding issue is there. I have to check that drive actually. Give me some time. I will check and come back to you. Okay.
Okay, sir.
I will come back to it. Let me check that drive actually. Might be some denotation is wrong actually. While see, I forgot to put the module 2 here. I have to put here the name as module 2 here. Where I've just put only module. I have to check that one once. I will check and I will get back to you.
Okay, sir.
Okay. So today's class was good for you, Hiranmai? You able to understand?
Yes, sir.
Okay. 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 If you have any doubt, you can ask me.
Okay, sir. No,
Okay.
sir. Today's class is fine.
Okay, so please get the tool installed in your computer. So you have a Windows or a MacBook.
Windows, sir.
Okay, then fine. So get the install. So in that one, a video will be there. Cadence installation video. You can use that installation video by going into the link. You can download the files, download all the files, Cadence Virtuoso, VMware, and the WinRAR file. Install all those things, VMware and WinRAR in your system, and then you have to extract that Cadence Virtuoso file to your system. Then only you will able to do. So just watch that video. If you have a difficulty, let me know. I will help you out. Okay.
Okay, sir.
Yeah, Nageshwar, you are having a issue. Can you just show me your system so that I can help you out?
Yes, sir. I just logged through mobile, sir, today.
Okay.
Yeah,
Now,
yeah.
Nageshwar,
No
do one
problem.
thing. You that downloaded that VMware file, right? Install
Yes,
that
sir.
VMware file inside your computer. Just do that
Okay.
yellow logo file is there, na? VMware
Yes,
file. This file. This one.
yes, sir.
That this one. This logo file. Install this in your system.
Sure, sure.
Install it in your
I already
system.
have. I already have that file, sir.
Then what is the issue? Then you can just click on this one and you can go inside this one and open that cadence file. I think then it should be fine for you to run. Then what is the issue then if you have the
It
file?
is showing that no files are found. Something it is showing, sir. I have showed you previously, right?
I'm not getting, so it should not say that. Then mind the installation is not proper actually. You have to reinstall it again. Might be you have deleted some files. See, seeing a logo doesn't mean that it will run. You have to check the compatibility. Might be you have deleted some file by mistaken. So just
Okay.
so then uninstall it. Go to the control panel, program feature, uninstall, and then again reinstall this file, and then try to
Sure,
see
sure.
whether it is working or not. Okay.
Yeah, sure, sir.
Okay. Okay, then
Thank you.
everyone, we can end the session here and we will be meeting you the next class. If you have any doubt, you can ask me. I think 4 or 5 minutes are left. You can ask me any doubt you have. Nilani, any doubt? Okay, okay, okay. Okay, so one thing I was supposed to discuss with you. In the Durga Puja time, there will be class with us actually. In the class, there will be a class actually in the Durga Puja. After Durga Puja time, there will be leave of 2 to 3 days, 3 to 4 days, maximum 3 days will be there. So we will be doing class over the Durga Puja. Is it okay for you guys? We can do, if you are comfortable, we can do in the morning also 1 hour. So evening might be you go for some outside, then we can do in the morning also. Is it fine for you guys? Hello, Danda, Hiranmai, Nilani, can tell. Hello. Okay, so in the time of Durga Puja, we will be trying to do in the. I will be telling the morning time. Don't worry, I will tell the morning time, Nilani. I will tell it to you. So from 15th till 18th, there will be no class. Actually, I will not be available from 15th to 18th, 3 days. That I will be trying to cover over the week, this weekday. I think 2 hours, 3 hours, that's either 1, 2 hours, or one, we will be able to do that one. No issue in the Durga Puja time. Okay. Okay, then everyone, we can end the session here and we will be meeting in the next class. Okay. And Hiranmai, please get your tools ready installed in your system. It will be helpful for you to understand everything. Okay. Okay, then we can end the session here. We can end the session here. Okay. Okay, everyone, and bye and good night. We'll meet in the next class. Okay.